Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our last part of this video series. We'll be discussing about the concept of telescope in this video. As I've explained earlier in simple microscope, the concept of magnification and visual angle. So we'll be discussing the same thing here, the concept of visual angle, and then we'll derive magnification using the concept of visual angle. We have learned that in order to derive magnification in simple microscope and compound microscope, we use alpha and beta. Here also we'll be using the concept of alpha and beta, but here the concept of alpha is a bit different than that of the concept that we have learned in simple microscope, so we'll be looking into that. If you just understand the basic concept, then this topic is very easy. And if you have gone through my simple microscope video, then this is absolutely easy. So try to grab the concept. If you grab the concept and if you memorize the formula, if they ask question in NEET from this part, then you can surely smash those. So without any further delay, let's jump into our concept building process and let's roll the intro. Okay, so let's start our study on the concept of telescope. There are two kinds of telescope we'll be learning here. That is, number one is a refracting telescope. Okay, and this is the most important one because mainly questions will be asked from this part. And number two is a reflecting telescope. So mainly we'll be focusing on this part, that is refracting telescope. But before that, let's understand what is telescope, the definition of telescope. As you can see on the screen, it's written that it is an optical instrument that is designed to make distant object appear nearer. Okay, what does telescope do? Telescope brings the object that is far away closer to the eye. This is the work of a telescope. Now if you think that telescope magnifies object, then that is absolutely wrong. Now don't get confused and puzzled here, because telescope does two things. It not only magnifies the object but also resolve the object. So let me write it down for you. Telescope does two things. Number one, it magnifies. It not only magnifies but also resolves. Now the concept of magnification you already know. What does resolving actually means? Now the concept of resolving is explained in the next chapter, that is wave optics, very clearly at the end of the chapter. So this is the concept related to that chapter, but since I'm explaining telescope, I will explain a little bit of resolving in an easy way so that it's easy for you to understand what does resolving actually means. So let's see, suppose this is an object and it is comprised of two separate objects. Okay, and when we look into this object very closely, or when we are closer to the object, we can see this object in a distinct, clear way. But when we see this object from a very far distance, then this object appears like this, that is, these two objects appear to be joined together and we don't see that object distinctly in a clear fashion. This occurs because of diffraction of light. You'll be learning that in wave optics. Okay, now if you want to view this object via telescope, and if telescope only magnifies object, then what we'll see? We'll see this object in magnified form. Now you'll be seeing it in this way. Okay, but still you won't see that this object is made up of two different objects as it is here. So this is just magnification. Okay, this is just magnification, but telescope doesn't do that. Telescope, what it will do, when you see this object via telescope, then what it will do, it will not only magnify but also resolve this. And you'll see these objects distinctly and clearly. I hope now it is clear. This is both magnification plus resolving. I'll give you another example. For example, you see moon in the sky at night. Okay, now you take a picture from your smartphone. You took the picture of the moon from the smartphone and you got it in this way. Now when you zoom this photo in your mobile, then what happens? You see the moon in a magnified form, but the image becomes hazy. You still don't see the details of the moon because you are just magnifying it without resolving it. But when you use a camera that has a telescope lens, then when you zoom it, then you see the cracks of the moon. Why? Because telescope not only magnifies but also resolve. Therefore, we can see the image more distinctly, clearly and bigger. Okay, I hope now the concept of magnification and resolving is clear. Okay, so this thing has been explained in the next chapter in details and it's quite amazing. Okay, now let's rub all this and move on. Now once you have understood that telescope magnifies and resolve things. Now let's look into what does visual angle do here. Okay, now visual angle, as you know, it is the angle subtended by the object at our eye. Okay, now if you look closely here, suppose this is the object. Now the visual angle that is subtended by this object is actually this angle, isn't it? And the visual angle subtended by this object is this one. I hope this much is clear. Now what does telescope do? Suppose this is the faraway object, as you can see it here. Telescope will bring this object closer to the eye. This is how it resolves. It never magnifies the image. In earlier case, we saw if this was the object, then using microscope, this object becomes like this. Okay, and then we say that the visual angle has increased. Earlier, it was like this, and then the visual angle increased. This was the work of microscope. But here we can see the visual angle is increasing in a different way. It is bringing the object closer, and then the visual angle is increasing. As you can see it here, as we are bringing the object closer to the eye, we can see the visual angle from the blue angle that it is increasing, and we know that when visual angle increases, the object appears bigger, isn't it? So this is how telescope does the work. Now, this is the object that we are viewing, isn't it? Therefore, this angle will be treated as alpha because this is the angle subtended by the original object, okay, without the use of telescope. And now by using the telescope, we pulled the object closer to our eye and we got the visual angle to be this one now. Therefore, this is the visual angle produced by the final image. Therefore, this angle will be treated as beta. I hope the concept of alpha beta is clear. We'll be looking into that, don't worry. This is just the basic concept of visual angle regarding to telescope. Now, as I've written it down for you, that any object that produces greater visual angle will appear bigger, and any object that produces smaller visual angle will appear smaller. Now, if you look here, the pink object produces a smaller angle, visual angle. Therefore, this object will appear smaller in the eye, but when we use telescope, then this object produces a greater visual angle, that is beta, which is greater than alpha. Therefore, we'll see the object in a bigger way. I hope this much is clear. Now let's note one thing. This is very, very important. Now let's understand one of the most important concept related to telescope. I've written it down here with note. This is very important. If it is said in the question that the telescope has a magnification power of 50, what does this actually means? Now, don't say that the magnification power of telescope is 50 means that the telescope will make the object 50 times bigger. That is absolutely wrong. This statement simply means that the telescope can bring the object 50 times closer to the observer. This is the concept that you need to understand. It does not magnify, it brings the object closer to the eye. Now, if the magnification power is 50, that means it is bringing the object 50 times closer to the observer. I hope now this is clear. So, I've written it down for you that don't think that it will make the object 50 times bigger, because these are the kind of question they can attack you in your exam in the form of objective question. Okay, this was asked in one of the year of JEE, that the magnification power of telescope is 100, then what does this actually mean? Okay, this was asked. So you need to be ready with the concept. Now, once you understood the concept of visual angle, the alpha and the beta, now you're ready to understand the magnification power of a telescope and how to derive that. So let's look into that. Now let's look into our refracting telescope concept. The thing that we need to understand is magnification. Okay, so we'll be deriving this formula for magnification. So let's see. We know magnification is equal to visual angle found by the final image, and we term that angle as beta. We have seen this in simple microscope. I've explained this in detail. And divided by visual angle found by object, and we take the visual angle found by object as alpha without the use of telescope. In the earlier case, we did this by telling that visual angle found by the object without the use of microscope. That was taken as alpha. But there, I have taken alpha as the visual angle found by the object when the object is placed at capital D, where capital D is distance of distinct vision, which is 25 centimeter. But here, we won't be taking alpha as the visual angle found by the object at D. Why? You need to understand this. Now, you're looking at a very distant object, for example, moon or Mars. So, if you want to check the visual angle found by the object without the use of telescope, then you'll get alpha. But can you bring the moon to capital D? That is distance of distinct vision? It's impossible. So we won't be using that formula because that's impractical. So we'll be using this formula, that is visual angle found by the object without the use of telescope. Okay, I hope this is clear. In the earlier case, the object was very small, so we can bring the object closer to our eye, that is 25 centimeter, and then we use to find visual angle found by the object without the use of microscope. I hope this much is clear. So we got alpha and we got beta. Once this concept is clear, now let's look into the diagram of refracting telescope. Now this is the diagram. Here also you can see that we have used two convex lenses. One is known as the objective lens, another is known as the eyepiece. In the earlier case, the objective lens was small and the eyepiece was big. Here the objective lens is big, as you can see. Now there's a reason why objective lens is big. I'll explain. The objective lens is bigger because bigger this lens, more will be the amount of rays entering through that lens. And more the amount of rays entering through the lens, greater will be the resolving power, or more brighter the object will be formed. Okay, because the intensity of the image that is formed is dependent on the number of rays that is coming and intersecting. Okay, this is the thing that you need to understand, and this thing has been explained in details in our next chapter, that is wave optics, where we'll see that resolving power is directly proportional to aperture. Aperture means this opening part of the lens. This is actually the aperture. Okay, I've explained what is aperture when I was explaining lenses, okay, and mirror, while I was teaching the earlier part of ray optics. Now once you know why the objective lens is bigger, you should be able to answer if it is asked in the question why objective lens in telescope is bigger. The answer will be to increase the resolving power of the telescope. Okay, now the formula that we'll be learning in the next chapter, that is resolving power. Okay, let me write it down for you. Resolving power, you'll see this in your next chapter. Resolving power is equal to A by 1.22 lambda, where A is the aperture. So you can see the resolving power is directly proportional to aperture. This is the formula. So this is taught in the next chapter. Don't worry about that. Now let's look into this diagram and see. As we know that the object that we are viewing is at a very high distance. Therefore, the rays that is coming from that object will be parallel. Simple as that. As I've written down here that the object is at infinity, therefore rays coming from it will be parallel. Now, as you can see it in the diagram, the rays that are coming are parallel but are not parallel to the principal axis. Now, I have explained this in my earlier video while I was explaining the terms related to lenses, that whenever the rays are parallel to principal axis, then the rays converge. If it is a convex lens, then the rays converge to focus. But if the rays are parallel to each other and they are not parallel to principal axis, then the rays converge on the focal plane. So as you can see, this is ray number 1, this is ray number 2. Both the rays are parallel. After refraction, they meet at focal plane. That is, this is the focus of the objective lens. As you can see, this is the object formed. This is the focal plane. Clear? Now, the image that is formed due to the objective lens will now act as a virtual object for the eyepiece. Now, if you look carefully, then you'll see that the image that is formed by the objective lens is actually between the focus of the eyepiece and the optical center of the eyepiece. Okay, what will happen whenever an object is placed between focus and optical center of the lens or of the convex lens? Then we know a virtual image is formed. Similarly, therefore you can see it here that if I take two rays, because we know we require two rays for formation of image. This is our first ray, and suppose this is our second ray. The first ray is parallel to principal axis, so after refraction it will pass through focus, as you can see it here. Okay, and the second ray is passing through the optical center, so it will go undeviated, and you can see that this ray and this ray are diverging in nature, therefore they will never meet. So if we extend this ray and this ray backward, you'll see that the rays meet at this point and we'll get a virtual image at that point, because the intersection is actually virtual in nature. This is not real intersection, and we got image to be formed here, and we term that image as A double dash B double dash. I hope this much is clear. If you have gone through my earlier video of microscope, then I have told you that whenever a convex lens is used and the object is placed between focus and optical center of the convex lens, then that convex lens actually acts as a simple microscope. Now if you look carefully, then you'll see that this object, the virtual object for the eyepiece, is actually placed between the focus and the optical center of the eyepiece. Therefore, this setup is actually acting as a simple microscope. Simple as that. Therefore, we can write here that eyepiece is basically acting as simple microscope. Now, things are very easy. Now let's derive the magnification of this telescope. In order to derive the magnification of telescope, we require alpha and beta. Now let's see. We know that alpha is the angle produced by the object when we are not using the telescope. So when we are not using the telescope, we will see these two rays, that is parallel rays, coming to our eyes. Therefore, this angle will be alpha, that is directly coming to our eyes when no telescope is used. So you can say if this is alpha, then this angle will also be alpha. Simple. Now, what will be beta? Let me rub this in order to create some space. Now, beta is the angle formed by the final image. Now, this is our final image. Now, this is the final image. Therefore, the angle subtended by this image at our eye will be beta. So you can see that this is the angle subtended at our eye, so this will be beta. Done. Now if you analyze the points, this is suppose O1 and this is suppose O2. Okay, so if you look into this O1, A dash and B dash, this triangle, then you'll see that tan alpha, which can be written as alpha because this object which is formed at focus is very small, because we know whenever the object is formed at focus, it is like a point object. We have seen this property. So this can be written as tan alpha as alpha, and we know the formula for tan alpha, it is perpendicular by base. Therefore we can write that alpha is equal to a dash b dash divided by, the base here is focal length of the objective, because this is actually the focal length of the objective. I hope this is clear. Now you can write this as negative a dash b dash because it is inverted, and tan beta can be written down as beta. Therefore beta can be written as, if you look into the triangle O2, a dash and b dash, then we'll see that beta will be perpendicular is a dash b dash. Okay, that can be taken as negative if you take into consideration the sign convention, and the base, this base is actually UE. Okay, so according to sign convention it should be minus UE. Therefore we got alpha and we got beta. Therefore magnification M can be written as beta by alpha, or minus a dash b dash by minus UE divided by minus a dash b dash by FO. Now if we solve this, then minus a dash b dash and minus a dash b dash would get cancelled, and we will get minus FO by UE. Okay, so we got magnification to be minus FO by UE. So let me write it down clearly for you, that magnification of telescope is minus FO by UE. This is the base formula. I've explained microscope, that is simple microscope, and compound microscope in the similar way. Okay, so this is the base formula which you need to remember. Now in many books you'll see that minus is not used. They have just written magnification is FO by UE. That is just the magnitude part. What does this negative sign signifies? The negative sign signifies that is the image that is formed is inverted in nature. Okay, I've explained this concept earlier. Whenever magnification is negative, that means the image formed is inverted in nature, nothing else. Okay, so this is simple. Now once you understand the base formula, we have seen earlier that there are two cases for simple microscope and compound microscope, that is maximum magnification in case of strained eyes and minimum magnification or normal magnification for relaxed eye. So we'll be looking into that. Now once you understand the base formula for telescope, then the two cases that we'll be learning is absolutely easy. It is similar to the concept that you have learned in simple microscope and compound microscope. If you have gone through that video, then this is just a piece of cake. So let's look into our case 1 and case 2. As you can see, the case 1 is for maximum magnification. Okay, and we know that for maximum magnification, our eyes get strained when we look into the image for a longer period of time. I've explained this. Okay, why our eyes get strained? Because the final image is formed at distance of distinct vision. Now how will this base formula change when the image is formed at distance of distinct vision, so that we get maximum magnification? So let's look into the diagram and things will be clear. So this is the diagram that we have gone through. This is our final image, isn't it? This final image should be formed at distance of distinct vision. Now we know the focal length of this eyepiece is FE. So we know the focal length of the eyepiece. Now we know the location of the final image, this one, and this should be equal to distance of distinct vision, isn't it? Now where should be this virtual object be kept in order to get the image at distance of distinct vision? We'll be looking into that. So how to find out that location of that virtual object? It's very easy. Use Lenz's formula. So we'll be using Lenz's formula. So let's see. We know Lenz's formula is given by 1 by F is equal to 1 by V minus 1 by U. Okay, we know the focal length of the eyepiece is plus FE, because focal length of convex lens is always positive. Now the final image distance is minus D. Now according to sign convention it should be minus. Okay, I've explained this while explaining simple microscope. Okay, minus of 1 by, now object distance, the virtual object should be kept at UE, that is minus UE according to the sign convention. We need to find out this UE. Okay, so if we solve this, we are going to get 1 by UE is equal to 1 by FE plus 1 by D. Okay, so we got this value. Now what we'll do is we'll put this value of 1 by UE in this base formula, so that we'll get the formula for maximum magnification. So let's look into that. So this will become M is equal to minus indicates that the final image is inverted. Okay, nothing else. And 1 by UE will be 1 by FE plus 1 by D. Now if you pull out the FE outside, okay, then it will be 1 plus FE by D. Okay, This is the final magnification, that is the magnification formula for the maximum magnitude. Okay, I hope this is clear. This is simple. Now let's look into our case 2, where we will find magnification, that is normal magnification, such that our eyes do not get strained, that is our eyes remains relaxed even if we look into the image for a longer period of time. Why is this? The reason is the final image is formed at infinity. Now we know that if the final image is formed at infinity, from the property of image formation in lens, we know whenever the image is formed at infinity, the object should be kept at focus. So simply what we can do is, actually the object distance should be at focal length, isn't it, to get the image at infinity. So what we will do, we'll just simply replace UE by FE. So we'll get minus FO by FE. Simple as that. How we got this? Simple, by using lens's formula. If we use lens formula, then also we'll get the same result. Like 1 by F, we know the focal length is that of the eyepiece, which will be positive according to sign convention, is equal to 1 by V. Now V, the final image is formed at infinity, so we'll write V as infinity, minus U will be minus of UE. So if we solve this, we are going to get 1 by UE is equal to 1 by FE. So we'll put the value of 1 by UE in this base formula and we will get this value. I hope the concept is clear. This is the formula for relaxed eye and this is the formula for strained eye, maximum magnification. I hope this is clear. Once this is clear, a little bit is still left, that is the length of the telescope. How to find out the length of the telescope? Now, in order to find the length of the telescope, we need to refer back to the diagram in order to make things clear. So if we go back to the diagram, we'll see that the length of the telescope is actually this length. Let me pick another color. So this length is actually the length of the telescope. I hope this is clear. So how to find out this length? The length of the telescope will be actually equal to this length. This is actually FO. If you look carefully, see the rays are coming from infinity. So the first image will be formed here at focus, isn't it? The focal plane. So this length is actually FO, isn't it? So this is FO and this part is UE, isn't it? I have written it down here. So we can say length of the telescope is actually FO plus UE. So let me write it down here. That is length is equal to magnitude of FO plus magnitude of UE. Okay, we'll not consider the sign convention because length is always taken as positive. So FO plus UE, this is the length of the telescope for normal case. Okay, this is normal case. So this is the first formula which is rarely used. The most important formula that is used to solve MCQ is this one. That is whenever the image is formed at infinity, that is relaxed case. So you can write it down for relaxed case. What should be the length of the telescope? It should be FO plus FE. Okay, how we got this? Let's go back to our diagram again and things will be absolutely clear. So this is our diagram. So always the image will be formed at FO for the first case. Why? Because the rays are always infinity, because it is coming from a large distance. So this distance is FO, but for relaxed case we know that this image is actually formed at FE, isn't it? So that we got the final image to be at infinity. So now for relaxed case scenario, we have seen that this UE, that is the object distance, virtual object distance, is formed at FE. Then only we get the final image at infinity, isn't it? So this will be converted to FE. Okay, that's why we got the length of the telescope to be FO plus FE. Simple as that. So if in the question UE is not mentioned and only FOFE is mentioned, then the length of the telescope will be found out using this formula. I hope this is clear. So this is all about the concept of telescope, refracting telescope, which is the most important telescope, and mostly questions are asked from this part. Now let's look into the concept of terrestrial telescope. It is similar to the telescope that we have learned. It's a little bit different because here we use an extra lens, as you can see it here. So we know what is objective lens, the lens that is kept near to the object, and we know this as eyepiece lens because we are looking through this lens, therefore it is known as eyepiece. The extra lens that we use here is this one, the middle one. So let's understand the functionality of that lens. Otherwise everything is similar to the telescope that we have learned. Now as the rays are coming from a far off object, therefore the rays will be parallel in nature, as you can see it here. These rays are parallel. Once these parallel rays comes and hits the convex lens, we know since these two rays are parallel in nature but are not parallel to the principal axis, therefore these two rays will converge at the focal plane, as you can see it here. So this is our focal plane and the object is formed at focus of the objective lens. Simple as that. And the object formed is real, inverted and diminished in nature. Now what we are doing is that we have taken this extra lens, and the image that is formed here will act as a virtual object for this middle lens. Okay, now we will keep this lens in such a way that the image that is formed here falls at a distance of 2f from this lens, where f is the focal length of this middle lens. I hope this is clear. And we know the property of the convex lens. When the object is kept at a distance of 2f from the convex lens, we know that whenever the object is kept at 2f in front of the convex lens, then the image formed is real, inverted and of the same size. Therefore, this virtual object will produce an image due to that middle lens here, and the image is of the same size and it is inverted in nature. Since this object is in this direction, so the image that is formed here will be upright. Okay, that is inverted in nature, and you can see the image is real. We have learned this property while going through the image formation rule due to lenses, that is convex lens. If you are clear with those properties of image formation due to lens, then this is absolutely easy. Once this is clear, now what we will do, this image that is produced here will now act as a virtual object for the eyepiece, isn't it? Now we will set the eyepiece in such a way that the image that is produced here, which is acting as the virtual object for the eyepiece, falls in between the focus of the eyepiece and the optical center. Now the focus of the eyepiece, I have marked it here. So this is the focus of the eyepiece. As you can see that the image that is formed here is between the focus of the eyepiece and optical center, and now you know what is going to happen. So this setup of the eyepiece along with this object in between focus and the optical center will now act as simple microscope. That means it will magnify this object, isn't it? And the image formed will be virtual and magnified in nature, as you can see it here. This is the image that is produced. I won't explain how the image is formed. We know all this technique and all the rules of image formation when the object is kept between focus and optical center. So this is all about terrestrial telescope. The only thing that you need to understand for terrestrial telescope is that it is a little bit different from Newtonian telescope. Now what is Newtonian telescope? The telescope that we have learned earlier was Newtonian telescope. So the first thing that you need to understand here is that in Newtonian telescope, image produced is inverted. Okay, you need to remember this. But in case of terrestrial telescope, the image formed is always upright. This is the first thing that you need to remember. And the second thing that you need to remember here is that the length of the telescope. How is the length of the telescope varying? Here the length of the telescope will be FO plus UE. This was the length of the telescope in the earlier case. Or we can say, in case of relaxed eye, we got the length of the telescope to be this one, FO plus FE. Okay, this was explained earlier. So this is the length of telescope in the earlier case. But what will be the length of the telescope for terrestrial telescope? The only difference that we can see here is the middle lens. And if you look carefully, then we will see that the length of the telescope is similar, except that there is a term 4f added to it, as you can see. So this length 2f this side and 2f this side. Okay, so this got added. So length of the terrestrial telescope is increased by 4f, as you can see it here. So this is for relaxed case and this is for a normal case. Just add 4f here. Okay, I hope this is clear. So just add 4f and you'll get the length of the terrestrial telescope. So this is all about the concept of terrestrial telescope and Newtonian telescope. I hope all the concept that I have discussed is super simple and you have understood all the concept. And the concept of reflecting telescope, which I haven't explained, I will not explain because I haven't seen questions coming from that part ever in NEET. So I will not explain reflecting telescope. If you just understand the part of Newtonian telescope and terrestrial telescope, then you are good to go. Because if questions are asked from telescope, then mostly questions are asked from this part. So this is all about telescope. Yeah, so this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.